Welcome to Unit 2, problem sets 3 through 4. Question 3. What we need to do here is we need to calculate the differences in electronegativity for each of the following highlighted bonds and show your work in the space provided. B, then we're going to label each bond highlighted as a nonpolar covalent, polar covalent, or ionic bond. Place our answers on the line provided. And then we're going to draw an arrow on the structure showing the direction of the bond dipole moment for each of the highlighted bonds. So in our first case here, we've got a carbon and a sulfur. Our electronegativity values for carbon is 2.5, for sulfur it's 2.5, and the difference here is 0. So there is no difference in electronegativity for those two, so this would be a non-polar covalent bond. Here we've got, in the next example, we've got zinc and carbon. In the case of carbon, our electronegativity value is 2.5. For zinc, it's 1.6. So the difference here is going to be 0.9. And this would then fall in the range of what's known as a polar covalent bond. Shown here. And in our last example, we've got carbon and chlorine. Chlorine's electronegativity value is 3.0, carbon's is 2.5, and therefore in this case our difference is 0.5, and this would be then classified as polar covalent. And so now what we need to do is we need to draw in an arrow to show the direction of the bond dipoles. In this case, we've got none, so there's going to be no line. Here, right, our zinc is less electronegative than our carbon, so our direction of our dipole is going to go in the direction of the more electronegative element. So in this case, it's going to go towards the carbon. And in our last example, carbon and chlorine, chlorine is more electronegative, and therefore our direction of our dipole is going to go in the direction of the chlorine shown there. That brings us to problem number 4, which is draw the Lewis structure for the following molecules and use an arrow to indicate the direction of the dipole moment as necessary. So right now what we're going to do is we're going to draw our Lewis structures, and then we're going to add any arrows for bond dipoles. We're not going to look at overall dipole at this point. It's just going to be the bond dipoles. So our first example here is going to be NF3. So the rules are the same as we saw on the previous video. So we've got one nitrogen. It's got 5 electrons. It's in column 5, so that's going to bring 5 electrons to the party. We've got fluorine. We've got 3 of those. It has 7 electrons, so that's 21. That's a total of 26 electrons. So our least electronegative element is going at the center. That's our nitrogen. We'll attach our 3 fluorines on the periphery. Put in our dots on the lines so we can see that right now we've got a total of 2, 4, 6 electrons, so we've got to put in 20 more. These start to go around the fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18. So now we're up to a total of 24 electrons. We've got 2 more to distribute, and then these now will go to the central atom. There's your 26 total electrons. And we look at this and say, are there any dipole moments or bond dipoles? And the answer is there are, because there is a difference in electronegativity between fluorine and nitrogen. And so your bond dipoles would be going in that direction, towards the fluorine, away from the nitrogen. Now we have methane. So we've got carbon. There's 1 of them. It brings 4 electrons to the party because it's in column 4. That's a total of 4. We have hydrogen, 4 of them at 1 electron apiece. That's 4. There's a total of 8 electrons. Our carbon goes at our center because our hydrogens can't. We attach our hydrogens to the periphery and add in our electrons so that we can see here. After a while, you can stop doing that, but it's good now as we're starting Lewis structures to see that each line does count for 2 electrons. We've got 2, 4, 6, 8. We needed 8, so we're good. The difference in electronegativity here is going to be very, very small. In this case, you wouldn't need to put in any bond dipoles because it's a non-polar covalent bond. Now we have CF4. So we have carbon. We've got one of them. It's in column 4, so it's going to have 4 electrons. We have fluorine. We've got 4 of them, bringing 7 electrons apiece in this case, which means you got a total of 28 electrons for them. That gets you to 32 electrons. Carbon is the least electronegative element of the 2. It goes at the center. Our fluorines go on the periphery. So now we have used, of our total of 32 electrons, 2, 4, 6, 8 of them. So we're down 8. So we've got to add the rest of them, the other 24 electrons around the periphery. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And so now we're at our total of 32 electrons. And there is a difference between the electronegativity of carbon and fluorine, so there will be bond dipoles from the carbon towards the fluorine in all cases, or in all bonds. Here we've got CHCl3. We've got a carbon, one of them. It has 4 electrons. We've got 1 hydrogen. That's at 1 electron, so that's 1 electron. And then we've got a chlorine. We have 3 of them times 7 electrons. That's 21. We add that up. That is 26 electrons total. Our least electronegative element technically is hydrogen, but it can't go at the center, so it's going to have to be the carbon. And we start adding our pieces onto the side. H, Cl, Cl, Cl. Put in our electrons that we have used to this point. So we've got 2, 4, 6, 8. That leaves us with 18 more to go. And so we're going to put those around the chlorines. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have all of our electrons in there. There is a slight difference in electronegativity between carbon and chlorine, so there will be a bond dipole going from the carbon to the more electronegative chlorine, shown like this. Now we have CH2O. So here we've got 1 carbon, 4 electrons, that's 4. And now we have an oxygen. We'll do our hydrogen first. We've got 2 of those at 1 apiece, that's 2. And then our oxygen, that's in column 6. So that's 6 total electrons with 1 of them. We add that up, that's 12. And so what we need to do is, in this case, our carbon is going to go at the center and start adding in our peripheral elements, like so. And in this case, we've got now 2, 4, 6 electrons. So we need to add 6 more. 2, 4, 6. So we've got all of our electrons in, but now we look around here, and the question is, do all of the atoms have a full octet? And if we look back at all our other examples, right, they did. Once we put everything in, everything had 8 electrons around that central atom. Here, we've got 2, 4, 6 around the central atom. Our oxygen has 2, 4, 6, 8, so it's happy, and so we have a problem here. And the way that we can fulfill this octet is we can potentially make a multiple bond here. So if we were to take this lone pair here and move it down into here to make a multiple bond, we would make the following Lewis structure. And that would give us a total of 2, 4, 6, 8, 10, 12. We still have our 12 electrons, but if you look at our carbon atom here now, we've got 2, 4, 6, 8 electrons around it. And this would be our Lewis structure that's the more proper structure than the one shown here, because now every atom has an octet. Our last one here, we've got what's known as methanol. So you can see we're ramping up the number of atoms in our molecules and getting more organic looking molecules. So we're going to have a carbon atom. We've got one of them times 4 electrons, which is 4. We've got our hydrogen atoms. We have 4 of them at 1 electron apiece. That's 4 electrons total. And we have an oxygen at 6 electrons. That's 6 total. And that gives us a total of 14 electrons here. In this case, our carbon is our least electronegative element, so it's going to go at the center. And we start adding our pieces on, so H, 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 O, and then our hydrogen like that. And the reason that we do it this way, if we were to put a hydrogen here, we can't, where are we going to put our oxygen? So our oxygen has to go somewhere between the carbon, between a carbon and a hydrogen. So this is what it would look like. So now let's add in our electrons and see where we stand. 2, 4, 6, 8, 10. So we're short 4. Now we go to atoms on the periphery that can have lone pairs, oxygen being one of them. It can handle 2. So there is a total of our 14 electrons. So we're good. Now what we need to do is double check to make sure everything has a full valence. So hydrogen does here, if you count, since it's a covalent bond, it's sharing this, so it's got 2. Our oxygen here, again, it's sharing the other electron with the other elements here, so it'd be 2, 4, 6, 8, so we're good there. Carbon, 2, 4, 6, 8, and all these hydrogens are good. And so this would be the proper Lewis structure in this case. And before I forget here, we've got a difference in electronegativity between carbon and oxygen, so therefore oxygen is more electronegative than carbon. Our dipole is going to go in the direction of the oxygen. If we go back to our formaldehyde example shown here, there's also a difference in electronegativity between our carbon and our oxygen, with oxygen being more electronegative. Therefore, the bond dipole is going in the direction of the oxygen from the carbon atom. And so these are our Lewis structures with our bond dipole. So the most important thing is get the total number of electrons, build your Lewis structure, and then also double check to make sure everything has a full valence. And if it doesn't, and you can use a multiple bond to create a full valence, then make sure you do so.